So as soon as it actually loads the little preview, then it'll let me go live. There we go.
Awesome.
Alright, I just went live. It should show the Kahoot screen.
Refresh it.
Yeah, it might take a second to load up.
Yeah, I think it's loading. Can't quite tell because it's loading, but it appears to be loading the right thing. Okay, yeah, it's going. I'm going to definitely make sure the audio.
Alright. Do you want to start the intro while I join the Kahoot so it can actually run classic mode? Quark?
Okay, so now I'm just buffering, and I'm not sure if that's my end or if that's your end.
I think it's mine.
Probably mine.
Because mine says it's buffering too. So people will probably experience buffering, but the stream will be there and it'll be available as like a watch later type thing instead of just the live stream. So if this is the best we got, then I guess we have to go with it because we're already 10 minutes in.
Yeah.
So if
yeah,
go ahead and do the intro and then we can get started.
Intro.
Or I can do the intro.
But
Doesn't really matter.
Yeah, you do.
Alright.
I don't actually know. I haven't done it before.
You're good. Alright, so welcome everyone to Study Bubbly's AP Chemistry live stream. Today we're gonna have a Kahoot that's gonna go over units 1 through 4 to help you review for your midterms. I'm Nico and I'm here with Quark. As we wait for everyone, as we wait for everyone to get ready and start joining the Kahoot challenge, we're just gonna go ahead and tell you to check out our website where we have our notes and podcasts, because while our stream and review is helpful, it doesn't go as in detail as our notes and podcasts do, so make sure you guys check those out and join our Discord server where we can offer more in-time help with any of your questions you might have for more subjects than just AP Chem. We also have other subjects such as AP Bio, Physics, Lang, Calculus, and some others. So we're gonna wait about another minute for people to join up in the Kahoot challenge, and then we're gonna go ahead and get started.
Two players.
Alright, so I know the stream's kind of lagging behind, but we're gonna go ahead and get started. If you guys aren't able to follow along well with the stream because of its lagging behind, this video will be up and posted after the live stream for you to rewatch for continued or repeated review, so you can go ahead and check that out after it has been posted because we're going to be explaining all the questions. But we're going to go ahead and get started. So the first question is, what is the name of VCl3? And you have a few different options here and not too much time, so go ahead and pick which one you think it is. Alright, and we can see that the answer was the blue diamond. I'm going to probably pronounce a lot of these wrong, so bear with me. Vanadium 3 chloride. And the reason it's named like that is because vanadium is a transition metal, and transition metals will have the Roman numeral after them for their charge. And chloride, similar like the other nonmetals such as oxygen and fluorine, will end in the "ide" suffix. So we'll go to the next question. Good job, whoever Fearless Oryx 52 is. The next question is, how many molecules are in 4 grams of sodium? So you have a few different options, and you can see that they're in a type of like scientific notation form. So we'll give you a little bit of time to answer those, and then we'll see which one is correct. All right, so all the answers were put in, so we can see that the answer was the red triangle, which is 5.5 times 10 to the 25th power. Quark, do you want to explain why that one was correct, or I can?
Sure. This one is correct because to get to molecules, you have to multiply. Well, first, you have to multiply. You have to turn 4 grams into moles, and then you have to multiply by Avogadro's constant, which is 6.023 times 10 to the 23rd.
Yep.
That, yeah, 23rd.
All right, so we'll
And
move
then,
on. Oh, sorry. You can keep explaining.
no,
Okay.
continue.
All right, so the next question is, what element is this? And you'll have a picture that shows the element. All right, so that graph that was up on the picture is a, correct me if I'm wrong, but I believe it's a photoelectric spectrum, and that shows the different ionization energies at each like level that the electrons are at. So those lower ones are all the S levels. The first one with the highest energy would be the S1 level, because that's the level that's closest to the nucleus of the atom. So it's the protons are going to have a stronger pull on the electrons there than, say, the 2p orbital, which is above the digit number 1. I believe that's a 2p orbital. Because, yep, that one, out of any of the other electron orbitals in this sulfur atom, is the farthest away from the protons, so they're going to have less of a pull on them. So we'll move on. Which of the following definitions are true? And you have definitions for homogeneous and heterogeneous, which apply to both mixtures and substances. You can kind of eliminate some of them right off the bat. So like the square, for example, homogeneous is clean versus heterogeneous being dirty. That doesn't really make much sense, so you can probably get rid of that one. And knowing that homogeneous and heterogeneous describes mixtures and solutions, you can rule out the blue option, the diamond, as well, because since they're mixtures and solutions, the homogeneous and heterogeneous wouldn't mean like pure elements or compounds. We have about 5 seconds left, so finish inputting your answers quick, and then we'll see what the correct one is. Alright, so the timer finished, and we can see that the answer was the yellow circle. Homogeneous is substance with same parts, and heterogeneous is substance with different parts. And Quark, do you want to explain that one?
So, the yellow substance. So, it's the yellow answer because homogeneous is the same substance, the same parts. Like, everything in it is the same. There's not. It's, if you think about like pond water, there's no scum in it really. That if there was scum in it, that'd be heterogeneous, and it would have different parts. And technically, and there's a test to do that, which is called the Tyndall effect.
Yep.
You just like shine light through it.
Alright, so we'll go ahead and move on. The next question is, which element is more electronegative, phosphorus or rubidium? And we have about 5 seconds left, so finish inputting your answers, and then we'll see what the right one is. Alright, we can see that the correct one was the red, phosphorus, and phosphorus is correct because if you remember, electronegativity is another one of the periodic trends, and electronegativity is like the measure of how much an atom has like attraction to its electrons. So atoms that are at the top right of the periodic table are the ones that have the least amount of electron levels, or yeah, energy levels, my bad, in their column, and they're also the ones that have the most amount of protons in their row, so they'll be able to attract all of the electrons much more than any of the atoms that are on the bottom left. So since phosphorus is closer to the top right, it has a higher electronegativity than rubidium. We'll move on to the next question. What is a valence electron? And your options are any captured electron, an electron that is in a bond, one of the outer 8 electrons, or the 8 closest electrons to the nucleus. Alright, so everyone finished answering, and we can see that the answer is the yellow circle, one of the outer 8 valence electrons. Quark. I mean, I guess there isn't really that much to explain. Valence electrons are just the outer electrons.
Yeah, outer 8, they do the bonding. That's all that's important. The rest of the electrons just don't matter.
Yep. Alright, so the next question is what type of bonds do these two compounds have? And the two compounds is CH4 and NaCl, which if you don't know, NaCl is common table salt.
Then CH4 would be methane.
Mm-hmm. Alright, so we have just a few seconds left and we'll be able to see what the right answer is. And we can see that the right answer was the blue diamond, nonpolar, covalent, and ionic bonds. So Quark, do you want to explain why the methane would have nonpolar and NaCl would have ionic?
Sure. So we're going to start with NaCl. So this is an ionic compound because it is a bonding between a metal and a nonmetal. It's usually gas, but there's not very many liquid elements anyway. But because of this, chlorine steals the electron from sodium, making it a stronger bond, and that's why it's ionic. Methane is a bond between a carbon and 4 hydrogens, which is about as nonpolar as it can get outside of the diatomic gases.
Mm-hmm.
Neither carbon nor hydrogen really have enough electronegativity to steal any electrons, so they're pretty squarely in the middle, meaning it is a nonpolar covalent bond.
Yep.
Instead of a polar one.
Mm-hmm. Alright, so we'll move on to the next question. What does mass spectroscopy do? And I probably pronounced that wrong, but oh well. And you have some options. There's it weighs elements. It separates elements by mass to charge ratio, which reveals the isotopes of the element. It determines just the charge of an element, or it determines just the isotopes of an element. So you have about 10 seconds left. Kind of guess what those are. And it ended because enough people shows the answers. And we can see that the answer is the blue diamond, which is it separates elements by mass to charge ratio and reveals the isotopes of an element. And that's because if you don't know what the mass spectrometer does, it'll ionize elements and then it'll accelerate them past in a magnetic field. And the magnetic field will push or pull them a certain amount inside the little tube that is the mass spectrometer, and that'll influence where they hit the end of it, which is a detection plate. So all of the atoms, correct me if I'm wrong, all of the atoms that have like the higher mass will hit more on one end than the other, and atoms with the lower mass will hit more on the opposite end. I believe the atoms with lower mass will be closer to the inside, but I could be wrong on that. Check the notes for
Yeah.
a clear understanding of that. But their masses are different because of the different amount of neutrons they have, which determines what isotope they are. So depending on how often a certain isotope will hit, there's a computer that will take the information from that to determine which isotopes of the element are more common. And yeah. So the next question is, what is Coulomb's law and what is it used for? So you have a few different options here, all of them having equations in them. So you have to figure out which equation is correct as long as what it's used for. And you have about 10 seconds left to figure that out, and then we'll go ahead and move on. And we can see that the correct answer was the red triangle, and that is F equals K times Q1 times Q2, and both of those are divided by R squared. And Coulomb's law determines the amount of energy between two atoms. If there really is more to explain for that, Quirk, do you want to explain more? It's kind of
So I'm
self-explanatory.
going to guess that most.
Huh?
I'm going to guess that most people, if they got it wrong, would have done the blue diamond. And you just have to remember that Coulomb's law has a constant in it, even though it's not. It's important. Nobody remembers that. And then, while it does calculate bond energy, it can also calculate the repulsion between two atoms.
Yep.
Well, yeah, bond energy has extra uses.
Mm-hmm.
And that's about it.
All right, so we'll move on to the next question. And it is, which of the following compounds has a higher lattice energy, NAF or KCl? So if you don't remember what the lattice energy is, that is the amount of energy that is released when an ionic solid forms from two gases. So with that in mind, you may be able to guess. And the answer was the red triangle, which is NAF versus KCl. And NAF have, I believe, yeah, sorry, NAF has a much, like, their differences in electronegativities is higher than it is between K and Cl. So that means that, first of all, it's going to take kind of more energy for them to be able to form. But that also means that because their electronegativities are so different, the amount of energy that's released when they finally become solids is going to be a lot higher than it is for KCl. Right? Yeah. Alright, so we'll move on. And the next question is, what type of alloy is the following compound? And you can see in that image there, it's relatively large enough to see. You have a lot of larger red circles followed by a few smaller blue circles dotted around in the middle. And you have about 5 seconds left. And we can see that the answer was the blue diamond, a substitutional alloy. Quark, do you want to explain why it's that versus interstitial or pure metal?
So, based on this diagram, it's obviously not a pure metal because there's two different color circles in there, molecules and all. But since they're not bonded to each other or anything, it's obviously not a pure metal. No, I don't think it would be if they're bonded. Well, it wouldn't be if they're bonded to each other anyway. It's not important. It's not interstitial because the blues have taken the exact place of where the reds were. They're not like in between the reds. They're not like squeezing into the little gaps. They're just substituting themselves.
Mm-hmm. Alright, so we'll move on. And the next question is, what is the Lewis dot structure for VOCl3? And you can see that there. I'm going to try to zoom in a bit so it's easier to see. That's about as far as I can zoom in. But you see we have 4 different Lewis dot structures there. And Some of them have single bonds while the others have double bonds. I didn't draw these, so Cork, if you want to explain a bit more while we wait for the timer to go down.
Yeah. Here's a tip, people. Never make Lewis dot multiple choice questions because I'm not fun to make up all the wrong ones for. But so some of them have more valence electrons, some of them have less. So you have to make sure that you count the number of electrons in VOCl3 before you start trying to make it, because otherwise you'll end up with something weird. And remember, for a nice quick rule for doing Lewis dot structures in general is just to remember that hydrogen will do its very best to have one bond, oxygen will have two, nitrogen will have three, and carbon will have four. So here that only applies for the oxygen because there's no hydrogen, nitrogen, or carbon in VOCl3. But
all right, so we can see from the answer that it was the red triangle, which is the top left Lewis dot structure, and that is the one where there are single bonds going to all of the chlorines, and they each have 3 lone pairs, and then there is a double bond going to the oxygen, which has 2 lone pairs. So, Quark, if you want to explain why it's that one.
Yeah, so if you look at the bottom left, you'll see that oxygen has one bond. As I said earlier, this is not what oxygen wants. And also, if you did count all of the electrons up, you would see that there's actually too many for what VOCl3 has. It's got one extra. Well, two extra. It's got an extra set. If you look at the bottom right, you'll see that oxygen doesn't even have a full octet shell. It's got 6, which is obviously wrong because you can't do that. Well, you can, but we're not allowed to do it.
Yeah.
And same thing if you look at the top right. Oxygen again only has 6, even though it has the double bond. So that just doesn't work because it's not alike.
Yep.
So that means the top left is correct, and it also is if you draw the entire structure.
All right, we'll move on to the next question. And it is, what is the Lewis dot structure for BF3? And again, I'll zoom in so you guys can kind of see this better, or at least zoom in as much as I can. But you can see that some of these have multiple Lewis dot structures, and that is because, correct me if I'm wrong, but I believe this is because that BF3 has resonance structures, which means that the Lewis dot structure can be written. Oh, what?
Yeah. It technically, I'm very sorry about this.
You're fine.
BF3 specifically doesn't actually have resonance. It's got like hybridization, but we're going to pretend it has resonance because I made a mistake and I didn't notice it until about 5 minutes ago.
All right.
And it's a little bit late.
It doesn't have resonance, but just for future reference, resonance is when the Lewis dot structure can be written in multiple different ways and still be correct. For example, if it's the single central element bonded to like 3 different other elements, and those elements can have double bonds, or at least one of them can have double bonds, that double bond could be in any of the 3 positions. So each of those different structures that equal like the same are called resonance structures.
Yeah. I believe a structure with like actual proper resonance will show up in a couple questions. So explain it better there. But when you write the resonance, you have to remember that you do have to write out all the resonance structures.
Yep.
Like, if you leave just 2 of them, it's not correct because it's not that the bond it's on one and then it's the other and then it's the next and then it goes back and then it's the other and then it's the next. It's on all 3 of them at the same time, just not as much.
Yep. So we can see from this that the correct answer was the square, and that was that top structure. So Corvic, if you want to explain that one.
Yeah. So if you look at this one actually this one has the correct number of electrons, and it has the resonance that boron tetrafluoride doesn't have, but we're going to pretend it does. And then it has all 3 resonance structures, which the second one doesn't, which is why that one is wrong. And then the third one has, if you look closely, you can see that boron has an extra lone pair. And boron being in the first period of the periodic table cannot expand its octet shell and cannot do that.
Yep.
Then the fourth one is just another way of writing resonance structures, but fluorine has a double bond in there, so it's wrong.
Mm-hmm. All right, so we'll go ahead and move on. Next question is, what is the hybridization of GeCl4? And you have a few different hybridization options. Excuse me, I had something caught in my throat for a hot second there. But you have about 5 seconds left, and then we'll see what the correct answer is. And we can see that it is the red triangle, which is sp3. And remember for bond hybridization that the number of hybridized orbitals is always going to be the total number of orbitals that's used to create them. So sp3 would have 4 hybridized orbitals, and we can see that for GeCl4 that would have like the 4 separate bonds. Quark, if you want to elaborate more, because I'm not the best at bond hybridization.
Yeah. Basically sp3. So you have the one s orbital, and then you have 3 p orbitals, which is a total of 4 orbitals. And that's how many orbitals you have for the 4 bonds, kind of. And so that's what it is. It's just sp3 hybridization. You just really add up the bonds, then count it out.
Yep.
And then sp4 hybridization just doesn't exist because there's only 3 p orbitals.
Yeah.
So that's just not real.
Alright, so we'll go ahead and move on. And the next question is, what is the Lewis dot structure for phosphite? And I'll try to zoom in on this again.
The resonance is back, and it's actually proper resonance this time.
Look at that. And you can see that these different structures also are in brackets with charges at the top, and that's because they are ions. So when you have to write Lewis dot structures for ions, you need to make sure that you put the entire structure in brackets and then designate the charge at the top right, similar to how you would in a superscript when just writing out the ion itself.
Yeah.
Alright, so we have a little bit of time left, except all the answers were put in, so now we have no more time left. And you can see that the correct answer was blue, which is that top one. Quark, if you want to explain why that is the correct one.
Yep. So this one, it's got it's got the correct number of electrons for when you add them all up. Phosphite being specifically PO3, which I'm sure you could have guessed by the various sections of the Lewis dot structures there that all had 1 phosphorus and 3 oxygens. So let's start at the bottom. For the bottom one, each of the charges, they're all -1. And it's just not -3. And that is why it is wrong. Because you do have to actually have the correct charge. It's very important. The next one, the second from the bottom one, the phosphorus, while it does have the full octet and it has all 8 electrons there, there's actually 26. Yeah, 26. Or either 26 or 24. You guys should know since you probably drew it out. Phosphorus, because it has the 3 orbital, it can expand its octet, and it does that to accommodate the extra electron that comes from just having those 4 elements there. The second, the top one's wrong because it doesn't have the charges, and those are important. You do need to have them. And the top one's right because it's got everything. Everyone is happy. All the electrons are used up, and the charges are correct. All the resonance is there. All is well.
Yep. Pretty much. So we'll go ahead and move on to the next question. And it is, what is the molecular geometry of a molecule with 2 lone pairs on the central atom and 3 bonding pairs? So you have different options here. You have trigonal, bipyramidal, T-shaped, linear, and bent. And these are all examples of the molecular structure based on the VSEPR model. And the VSEPR model takes into account a few different things: the valence electrons, the electron shell, the electrons themselves, their pairs, as well as the repulsions. And we can see that the correct answer was blue, T-shaped. And that is T-shaped because when they have the two lone pairs and the central atom has three bonding pairs, the atoms are pushed around in a way that will form a T. So the three bonding pairs will be sticking out in the T shape, I believe. And then the two lone pairs will be on that center atom, and they'll be kind of like sticking off to the sides, almost forming like a square type shape with the two top branches of the T. And that is how it keeps all of the repulsions to a minimum. So we'll move on to the next question. And that is, hydrogen bonding is a common example of which type of intermolecular force? And you have London dispersion forces, nonpolar molecular forces, which are also called dipole-induced dipole interactions. You have covalent bonds, and then you have dipole-dipole forces. And we can see that the correct answer was dipole-dipole forces. And the reason it isn't polar and nonpolar molecular forces, because at least one person picked that, is because hydrogen bonding involves like the intermolecular force between a hydrogen atom and then one of the highly electronegative nonmetals that are over on the top right, such as fluorine, nitrogen, and oxygen. And the reason it is dipole-dipole versus the polar and nonpolar is because that hydrogen with the highly electronegative atom causes that polar bond to form because the electronegativity difference is so high, and that is why it is dipole-dipole versus polar and nonpolar. And hydrogen bonding, just as a side thing, is also one of the stronger forms of dipole-dipole forces because it's with the H in that highly electronegative atom. What? Did you say something, or was your mic just being whack?
Alright, my mic's just being whack. It
Ah.
doesn't like it.
Alright, so the next question was, which of the following defines network solids? And the answer was chosen right away because someone clicked something. But we can see that the answer is ionic solids containing strong covalent bonds to form a giant molecule is the network solids. And the other ones, the green, the noble gas one, is an example of the group 8. I think it's just group 8 forces, actually, group 8 solids, because those are all made up with the group 8 elements, those noble gases. The blue, the substances with strong attractive forces between oppositely charged ions. Like Quirk mentioned earlier, those are the ionic solids. Those form like such as NaCl and whatnot, where it's the metals on the left side and nonmetals on the right. And then the triangle is solids with strong covalent bonds but relatively weak intermolecular forces. And those, correct me if I'm wrong, because I think I may be, but those would be an example of not metallic solids. Those would be an example of molecular solids. There we go.
Yeah, I think so. I'm not the best with larger scale things.
All right, so moving on, the next question is describe capillary action in liquids. And right away you can probably eliminate the blue triangle, liquid's tendency to flow away from caterpillars, because, well, that doesn't really happen.
I mean, with the caterpillar hydrophobic, it might happen a little bit.
You know what? You're not wrong. If you have hydrophobic caterpillars, they probably would run away from liquids. But we can see that the actual correct answer, even though someone did pick the blue diamond, is actually the green square, which is the rising of a liquid in a narrow container due to adhesion and cohesion forces. Quark, do you want to explain that one a little bit more?
So I'm gonna let you take this one because
All right.
I
Yeah, you're
do
good.
not know the exact specifics.
All right, so for the liquids, normally it's just polar liquids that can do that, so we'll use water as an example. But water, as you know, has high cohesion and adhesion forces, and cohesion is the tendency for the water to stick to itself through hydrogen bonding, and adhesion is its tendency to stick to other surfaces, so other surfaces that are polar the water will be able to stick to. So in a narrow container, water through adhesion will stick to the sides of the container and extend up as far as it can on any of the sides because it keeps pulling itself up. And as it pulls itself up, its cohesion property will cause like the water molecules that are in the center, not near the walls, to grab onto the water molecules that are climbing the walls. So the water will essentially just start crawling its way up the narrow tube. And that mixed with pressure is how something like a straw would work, where the water will climb its way up. But in general, just if you put water in a narrow tube, you'll see it move up a little bit. And that's also how plants are able to move water around throughout like their, I think it's called phylum. I could be wrong. I probably pronounced it wrong. Phylum, all right. So that's how plants are able to move water around through that, because those are narrow tubes within them that the water, through capillary action, can just like move around itself. So the next question is, what is the ideal gas law? And you have a few different equations here and not too much time. And we can see that the correct answer was the red triangle, which is P times V equals N times RT. And Quark, if you want to explain that one.
So the ideal gas law is a combination of some other laws that are less important that you really don't need to memorize because you can just derive them if you ever need them. But so it's basically pressure times volume is equal to the number of moles times the gas constant times the temperature, and this is the equation you use that to determine really anything that involves gases because as pressure goes up, volume goes down, temperature goes up, moles go down. Really, that's how life works. And you really just need to have it memorized. There's not much else to say there.
Yeah. All right, so we'll move on. And the next question is combinations of components with variable composition that can consist of pure substances and molecules define which of these terms? And the terms are chromatography, mixtures, crystalline solids, or metallic solids. And we can see that the correct answer was mixtures. And it wasn't chromatography because chromatography is a way to separate mixtures and solutions into their pure substances, such as with paper chromatography, where you stick the paper in the solution and you can see like what portions of it travel farther up the paper based on their colors. Metallic
It's very cool and
solids,
fun to do things.
it is very cool. Metallic solids and crystalline solids are both examples of different molecules with properties of solids, so that's not really like a combination of components with pure substances and molecules, because they essentially are just the pure substances and molecules. But mixtures are those different combinations of different molecules in the same one component. But we'll move on. And the next question is, which of the following describes saturated solutions? So you have a few different options here and not too much time. We've talked about solutions briefly before. They're similar to solutions, or not, they are solutions. They're similar to mixtures, and they, like the mixtures, can be homogeneous or heterogeneous, where they're made up of like all of some of the same stuff, or they're just made up of different molecules and atoms. And we can see that the correct answer was the blue diamond, solutions in which no more solute can be dissolved. Quark, do you want to explain that one?
Sure. So a saturated solution is, well, it's a solution in which no more solute can be dissolved. It's basically when the solution has dissolved so much solute that it just can't anymore. Everything has done its job. There's nothing left in the solute solution that actually has the capacity to dissolve more solute because it's all been taken by the other solute. Usually this does take a while. You have to add like a lot of salt to water to get that to happen. I did try it once. It took forever. So solutions containing more solute that's possible to dissolve, those are super saturated, and then ones that have more solute can continue to be added dissolved. They're just not saturated solutions.
Yep.
And yeah.
All right, so we'll move on because we're starting to get short on time. What does the emission of electrons from the surface of a metal when it is struck by light refer to? So you have a few different options. They're all kind of similar except for spectroscopy, which we talked about earlier, so you can rule that one out. And we can also see that the correct answer was photoelectric effect, which is the yellow square. And it's photoelectric effect because, one, that is the term for it, but it's not the dual nature of light, because the dual nature of light is actually something that was found out based on findings by people such as Planck and Einstein, and it's the idea that electromagnetic radiation can be shown in characteristics of particulate matter as well as in wave properties, which was something that was like really important and controversial because previously it was only thought that characteristics of light could only be seen in wave properties because of that separation of energy and matter. And it's not the electromagnetic spectrum, because that's just the overall spectrum that categorizes different wavelengths based on their length and their frequencies. So that is why the correct answer would be photoelectric effect. Moving on. The next question is, what type of reaction is C3H8 plus 5O2, which produces 3CO2 plus 4H2O? And we can see that the correct answer was a combustion reaction. Quark, do you want to explain that one?
Sure. So usually anytime you see carbon dioxide and water as products, it's usually combustion reaction because that's what happens when you burn things. You get water vapor and CO2. Specifically, C3H8 is propane, which makes it kind of more obvious. There's not much else you do to propane. But really, so single replacement isn't exactly what's possible here. It's when so actually we're going to double replacement first. That's when you have compound AB and compound CD, and they switch, and you get AD and CB. Single replacement is actually what's possible here is when you have compound AB and compound C, and then you get A, C, and B, I think.
Mm-hmm.
And then decomposition, you kind of need, we don't need one reactant for it, but it's just when something falls apart. And it's obviously not falling apart here because we have two entirely different compounds as products. So it's combustion because we burnt propane.
Yep, and I don't know if you mentioned this earlier because I was trying to fix the Kahoot thing on my phone, but combustion reactions will always have a different amount of CH plus O2 as the reactants and will always produce CO2 and H2O. So, moving on. The next question is, which of the following compounds is insoluble? And there's AgCl, NaF, KF, and SO4 2-. And we can see that the correct answer was AgCl. And Quark, do you want to explain that one? If
Sure.
not, I can.
So, you're not. I can give it. You're not expected to memorize like all the solubility rules because there's a lot, and that would suck. Really, some of the most basic things are that sodium is almost always soluble, and that the exceptions to almost every solubility rule are silver and lead. And So silver chloride is silver chloride. It doesn't have a nitrate, which makes most things soluble. So it's insoluble. Potassium fluoride and sulfate. Like there's slightly more complicated solubility rules to why they're soluble, but that's not important when you know that silver chloride is silver and therefore will never dissolve.
Mm-hmm.
Well, it might. It tries very hard not to.
Yeah. Alright, so we'll go ahead and move on. The next question is the delivery of a certain volume of a solution of a known concentration into a solution with an analyte is a what? And your options are precipitate reaction, indicator, net ionic equation, and titration. And you can tell right away that precipitation reaction and net ionic equation are both going to be things that can be like written out as a reaction equation. So based on the type of question, you can kind of rule those two out as the option. And in about 5 seconds, we'll get the right answer, and we can see that it is titration, the yellow circle, and that is because, first of all, that is what titration is. It's when you take that specific amount of a solution in a known concentration, and I lost my train of thought, and you put it into a solution with an analyte. It can't be the other two, the precipitation and the net ionic, because both of those are just examples of different reactions and equations for those reactions. And then the indicator is involved in titration, but the indicator just serves as something that'll make the titration, or I believe it's called a titrant, which is the one that is added. It'll make it change color once the titration meets its equivalence point, so you know that it's done. So while it is involved in titration, it's not an example of what titration actually is.
And you don't always use an indicator in every titration because in some cases, I believe it's usually like redox reactions.
Yep.
The compound will change color on its own, and you just don't need it.
Yep. So the next question is, which of the following describes precipitation reactions? And here you have actual examples of 4 different reactions. The first one is reactions where one or more elements will transfer between elements/molecules. There's reactions involving the transfer of protons between proton donors and acceptors. There's reactions involving the combination of 2 elements to make a molecule. And then there's reactions involving the mixing of 2 solutions to form a solid. So the timer isn't up, but we're going to go ahead and skip because we're running low on time. And we can see that the correct answer was the green square, reactions involving the mixing of 2 solutions to form a solid. And that's what precipitation reactions are, and that solid that forms is called the precipitate, but it wasn't the blue one because that describes acid-base reactions, where the proton donors would be the acids that have high concentrations of H+ ions, and the acceptors would be the bases who have high concentrations of OH- ions, sorry. And that triangle where one or more elements will transfer between elements and molecules, that was like similar to the combustion reaction we talked about before, where the elements are just transferring around and changing. And then reactions involving the combination of 2 elements to make a molecule, that was an example of just like a base reaction, I guess. Something like an ionic reaction where it would be Na and Cl to form NaCl table salt. So we'll move on. The next question is, what are the Bronsted-Lowry acids and bases defined as? And I kind of gave that away in the last question. So we'll go ahead and skip again for time's sake. And we can see that the answer is the red triangle. Acids are H+ donors and bases are H+ acceptors. And bases act as those H+ acceptors because they have more high concentration in OH-, which, as it accepts the H+, will become H2O, because that's how it works.
Yeah.
And yeah.
Bases just can't donate what they usually don't have.
Mm-hmm. So we'll move on to the next question, and it is, oh, that's a long question. 3ZNS plus 2ALP will produce ZNP plus ALS. And if you have 10 grams of ZNS and 7 grams of ALP, how much ZNP will the reaction produce? So that's one that you just have to math out. What?
If you look at it, you'll see, if you look at the question, you'll see it's a little weird. I didn't notice until before we like right as we started streaming. The question didn't copy quite right, so the subscript
Oh,
isn't there. But just pretend it is. The coefficients are still right. The subscript just disappeared.
yeah. All right, so that's one you'd have to math out using stoichiometry, where you can convert different units to other units within a reaction by taking the mole ratio of the reactants and products that you're trying to convert. And we have a more detailed description and examples of how to do that within our, I believe it's the Unit 4 notes. So head to our website to check those out. But since this is just a math problem and we're running low on time, we're going to go ahead and move on.
Yep.
And the last problem is, for monatomic ions, what will the oxidation state always equal? And for time's sake, we're going to skip, and we can see that the answer is the blue diamond, the charge of the ion. Quark, do you want to explain that one? If not, I can.
I'm going to let you do this one because I was not good at remembering which oxidation state was which and why.
All right, there is a set of rules for writing oxidation states, and one of the main rules is that for monatomic ions, the charge of the ion will always equal its oxidation state. And some examples of that would be things like Na plus or Cl minus, because since those are just singular atoms, the oxidation state for them is just going to equal the charge. And the oxidation state itself is just a method for tracking the electrons in redox reactions. And it's just like it assigns the specific amount of electrons to particular atoms, even though that they're shared in the redox reaction. So it's just helpful for like balancing them out and doing stoichiometry with them and whatnot. But since the monatomic ions already have their own charges, the oxidation state is just set as their charge. So that was the last of the questions for our review. We didn't have any sort of FRQ or long answer questions, but we don't really have time to go over one. So yeah. Quark, if you want to do the outro, or if not, I can. Up to you.
Again, I don't know it, so.
All right. But yeah, thank you guys for joining us. This has been the Study Bubbly AP Chemistry midterm review over units 1 through 4. And we hope you will like this and subscribe, share it with your friends so we can help out more people with this. And also check out our website where we have the more detailed notes as well as podcasts for all 4 of these units. And we'll also be releasing study guides that help summarize the key points of both these 4 units in chemistry as well as a lot of other AP subjects such as, like I mentioned earlier, bio, lang, history, government, etc. We have 3 live streams still for today, so stay tuned for announcements on those on our different social medias and our Discord, which you should follow and check out. On our Discord, we offer live help, as mostly 24/7. We do have to sleep, so we can't always get to you. But yeah, thank you guys for joining us, and we hope you'll listen to us again soon. So see ya.
I
Alright, so I'm going to keep the stream going for now because for Lang last time I ended it like this because we had another stream directly after and it cut out like the last portion of the stream because it's lagging so far behind because my internet's garbage.
Yeah.
But we don't
Oh,
have
yeah.
another stream today